Okay, then let's start. Let me start the timer. Yeah, hi everyone. My name is Olga Andreeva. I'm a senior software engineer at NVIDIA. And I'm working on Dynamo, our open source inferencing solution for data center scale. It's actually not my first open source project. I used to contribute to, well, still periodically, contribute to PyTorch. PyTorch was my first open source project I got involved in and fell in love with the open source. Then I spent some time contributing to NVIDIA Triton inference server solution, and now it's Dynamo, so third time is a charm, I guess. You can see that it's not only my name, which is on this presentation. This talk was prepared in collaboration with Ryan McCormick, who is my colleague. Unfortunately, he couldn't come, but he sends his high and warm regards, and we both are looking forward to your contributions to our open source stack. So let's start from the beginning. Generative AI. Personally, use generative AI every day, find it useful. I really like generative AI for multiple reasons. One of those is that it really opened up opportunities for multiple people to contribute because it's rapidly changing the enterprise level software systems. Why? Well, modern LLM, as we all know, are no longer fit into the single GPU modalities, right? We need multiple GPUs. So basically, if you think about DeepSeek R1, we actually also need multiple nodes to be able to deploy it comfortably at the production. So when we deploy our single element to multiple GPUs, we need to chunk it, right? And there are multiple approaches for that. Pipeline parallelism, tensor parallelism, all those are become useful at those applications, but those are also raise important issues. How do we navigate between those chunks and shards? How do we ensure that communication which is happening between those shards are following our latency constraints? How we confirm that our throughput is at the level we expect? So deployment and development complexity of those solutions is rising, but also it opened up a lot of opportunities for optimizations and contributions to the open software. So given all those motivations in mind, what engineers are looking into is how do we need to approach this problem from the beginning, right, and redesign solutions we had in mind. So before we go into that realm, we need to think about requirements and challenges that come into the picture. So first of all, we want to support advanced AI capabilities. And even today, during our keynote sessions, you heard a lot about agentic workflows. Agentic workflows bring a lot of things like we need to serve multiple LLMs. Each of them are dedicated to separate workloads. We need to support tool use. We need to support constraint decoding. Besides that, we need to think about inference time compute. We also need to think about multimodal LLMs, right? Because generative AI is now not only text in, text out, but also we can ask it to analyze pictures. We can ask it to summarize videos. We can pretty much ask it to do anything. And for that, we need to support multiple modalities. For all those things, we need to think about dynamic memory needs, how to properly allocate it, how to manage that, which basically hardware to use for different things. As I already mentioned, we need to scale beyond single GPU limits efficiently. We need to make sure that communication which is happening is efficient. We don't want to violate any SLAs you have for your enterprise stack. We also want to optimize developer and system experience. We can do a lot of things, right? But if it's practically unusable and it's hard to people to deploy or use your stack, people will simply not use it anymore. So all those things, they need to be thought of and carefully approached. So our engineers and tech leadership try to approach it from three different perspectives: from scheduling, memory management, data transfer. So when they think about scheduling, think about not only how do we schedule the request to different GPU, but also how do we schedule what GPUs do what. Basically, we need to also think about network surges, right? There are times of the day when you have low level of the requests coming into your server, and there are times of the day when you have surge in those requests coming. Can we dynamically schedule extra GPUs you have at hand to basically be capable to serve every single user that wants to get useful information from your service? Memory management, right? When we chunk our model, there is an optimization technique called KV cache. I'll talk about this later, but we want to make sure we're properly computing and storing those KV caches from those chunks of the models, right, which are spread between multiple GPUs. Data transfer, right? We want to efficiently transfer the data. We want to efficiently transfer the request, any events that happening in your software system. All that should be under the constraint that you set it to be, and you want to get the speed of light. And all of those three directions, they basically help us to look into distributed inference serving. And we want to approach the distributed inference serving from the actual true distribution, where we not only serve multiple replicas of the model, we also want to look in the model and look at this model, what does it do, and can we separate, even inside the model paradigm, can we separate more workloads and assign it to different hardware. So here's how the Dynamo came to be. Here's the high-level architecture. All those pictures are in the slides, I shared them. So all those pictures are also available in our GitHub repository. So basically, there are multiple components, as you can see. There is API server. We support OpenAI, compatible endpoint, Llama Stake API, many more. We have smart routing. We also have a basic routing, like round robin and random routing. I'll talk about this later in the talk. We have multiple dedicated workers to approach your LLM serving task. We have the event plane. So when KV caches are stored, there are events that the worker emits, and we want to collect them and subscribe them and update KV cache trees. We also have that. For KV cache management, there are more optimizations than just building the KV cache tree. We can also offload it to the host memory or on the disk. Together with Dynamo, Nixel was released. This is an NVIDIA inference transfer engine, and that allows you to do low latency interconnect agnostic multi-node data transfer. We also have a planner, and planner that is related to the idea that I talked about. Basically, during the network search, can we reprogram some of the GPU, do different stuff, and achieve higher utilization than it was before. So let's look at the architecture step by step. So here's the simple idea. So we have our API server, we have our router and multiple workers. Dynamo is a Rust native, but we also have Python bindings because a lot of AI and machine learning board lives on Python. So we love our AI engineers. We would like them to feel comfortable, and we don't want them to relearn any new languages. So we provide options through Python bindings. So what's happening under the hood? So when you want to start and deploy your graph, basically all the components, they need to register themselves in the discovery plane. And we use etcd for that. So basically, API server registers itself in the etcd plane and watches for the routers and workers to come up. Router, same, it registers itself and watches for the workers. However you specified, how many workers you specified initially, it's going to watch for them, for all the workers to be live and ready to serve your model. And workers' task is basically to register themselves and initialize your LLM engine. So it would split your model in chunks, right, and dedicate the chunks to the separate workers and wait for all the workers to come up and be discoverable through the discovery plane. And when all of this is set and ready to go, you can send your request in. What happens with the request plane, right? Front-end task is to translate your OpenAI request, which comes in, into the Dynamo requests. Then those requests need to be routed to a particular worker. So that is going to be sent to the router. Router will decide based on the strategy you picked, the best worker where to send the request. And basically, the worker will execute the request. And request plane is implemented through NATS.io and TCP. Next, the event plane. So we use event plane. It's actually a very powerful thing to utilize. So every point, every component in Dynamo can emit an event, right? And every component in Dynamo can subscribe to listen to those events and do whatever it needs to be done when a particular event happening, such that when, for example, KV cache block is full, right, and it's ready to be stored, the store event is going to be emitted, right? The router or whoever will pick up this event and update the tree and the global view of which worker store what KV caches. So that's done through the event plane. And then finally, the heavy chunk is the data plane supported through Nixel. So we front-end will use request bus for small transfers and Nixel for larger transfers, and it will send the data in the request directly to the worker and bypassing the router. So router, as you can see, does not really need to participate in the data movement because it's not particularly its job in that particular scenario. So I talked about KV cache. Let's look briefly at how it's done. So if you look at the LLMs, right, there is a context phase, basically your prompt. It can be very long, it can be very short, but it all needs to be loaded to the LLM, and all the KV caches and attention matrices needs to be computed. This is a very compute-bound operation. However, when all of this is loaded into the memory, we can start generating and producing new tokens. And as it turned out, this is a very different style and type of operation. It's very memory bandwidth bound. And what can we do? Well, there was a research paper which we take a look into, and we implemented the approach called disaggregated serving. Basically, what it means is we take the prefill phase, we put it on a separate set of GPUs, and then when prefill is ready, all the computed KV cache will be transferred through the Nixel, through the data plane to the dedicated generate workers, which job is basically to generate our tokens one by one. And the beauty of this approach is that you can scale every part independently, and it becomes very useful, especially at the data center level workloads. Now let's briefly mention dynamic GPU scheduling and smart routing. Here is, you can see IDEA, which I briefly mentioned, and which is responsibility of our planner. So think about, you dedicate your small chunk of hardware for the context phase, and that's the prefill phase, and they're responsible for computing KV caches, and send them to the bigger chunk of your hardware world, which is responsible for generation. When you surge in the summarization, for example, request comes, right, you can see that utilization of the prefill phase becomes almost like that's 100%. However, our generation phase is underutilized. That's not good. And why is this happening? Well, summarization requests are known for providing long context, right? You want to send multiple documents, multiple data to your GPUs, and they need to process, like convert it to tokens, process it, and compute KV caches. So what can we do? How about we take some part of GPUs dedicated for the generation and reassign it to the context phase. That's what's available in Dynamo through Planner. You can try it now, see how it works. Now let's talk about routing, request routing. So we support the basic, well-known routing algorithm, random routing, right? When there is no clear algorithm or better where to send the request, right? Your request 1 can go to GPU 2, your request 2 can go, in this case, to GPU 1. It doesn't really matter. We support that, but what's happening, especially with the LLM workloads, imagine that your request 1 and request 2 have almost similar context, right? In this situation, your GPU 2 has already computed all the context, KV caches, and attention map on GPU 2. It stored it on GPU 2. Why not utilize it the same for request 2, where context matches at 90%, for example, right? Random routing will ignore that completely, and GPU 1 will have to recalculate, redo all the same compilation again. Round robin. Round robin, same problem. However, it tries to have a more or less balanced request sent to all of your hardware. However, there is the problem of we need to recompute KV caches, and we have a KV cache miss basically if requests with the high context match are going to be sent to different GPUs. At Dynamo, we also support something that is called direct routing. In this scenario, you can basically control where to send your request to which GPUs. So how we can use it? We can actually do something like a smart router. And that will solve the issue where we need to recompute KV cache, meaning we would not need to recompute the full KV cache. If there are GPUs or conglomerate of GPUs that have high KV cache match with your incoming request, right? You can simply route it to a particular GPU. You can also do something like next level. You can take not only KV cache match, but also a load into picture and provide your custom cost function. We support that. You can provide your custom cost function for smart routing, and you can incorporate the load into the calculation. And instead of, for example, sending your next request to GPU 3 with KV match at 75%, you can reroute it to KV match to GPU 2, right, which has lower load, but KV cache match is also still at 50%. That means we need to recalculate less amount of KV cache. So Nixel was also released together with Dynamo, and it's a separate source. So if you're interested in communication, you're more than welcome to become a contributor to our Nixel library. So what it is, I would like to think about it as our logistic center, right? I do not really care, well, I do care, but as a developer, for example, ML developer, when I only want to deploy my LLM, and have KV caches be transferred from GPU to GPU, from GPU to host, or even from GPU to local file storage, right? I don't really want to go into those niche level and specify, okay, in this particular situation, use EX to send data from GPU to GPU, but for GPU to SSD, please use other backend, right? I don't care. That's where Nixel comes very handy and useful. So it will pick for you the best strategy depending on where you need to send your data and where you need to send it from. It provides a very handy interface where you only need to specify descriptors, basically the memory location, right, and what is stored. And for each of your process, you also only need to start the thing called Nixel engine. And then they'll figure out the communication themselves. They pick the proper backend for the communication and make sure that the communication and data transfer satisfies your latency constraint. Now moving to disaggregated serving. So as I mentioned before, we can split prefill and decode. Prefill is compute bound, decode is memory bound. Prefill is typically measured in time to first token. Well, if you think about it, how much time does it took to compute all the KV caches and produce the first token, right? And then the decode phase is measured by inter-token latency, so basically how fast the next token can be generated, right? We can split them, and we can now scale them independently, so we can have multiple prefill workers, multiple decode workers. You can utilize even different tensor parallelism. So you can utilize tensor parallelism 4 for prefill, but tensor parallelism 2 for decode phase. That's all available to you. You can do whatever you want. It also cuts costs. You can think about this. You can suit the most appropriate GPUs for memory-bound cases and the other stack of GPUs for compute-bound cases. There are a lot of blogs online, and some of them share how different people and organizations approach this problem. Now, if you briefly remember, I mentioned the multi-model case, right? Well, we can disaggregate these two and even further. If you think about this in the paradigm of besides computing attention map, we also now have an image or a video which we need to convert and provide an embedding for it. Well, this also can be put into a different stack of GPUs, right? And you also can scale them separately. Besides that, you can also apply different level of optimizations on the encode phase, right? If you see the same image you saw before, you can apply exact caching, right? And not recompute that anymore, which will save your latency and increase the throughput. Now, some of the examples. So I provided the link on the presentation to the examples folder. Basically, we have a dedicated examples folder. There are multiple of them. This one focuses on LLM, and you can see that there are 5 instructions, but they're all different. So basically, to deploy your graph, you only need one instruction, Dynamo serve, and then you provide an entry point to the graph, and you provide the config file. And that will cover 4 cases: aggregated serving with KV routing, disaggregated serving, and disaggregated serving with KV routing. The difference comes in the YAML file, and those are only small different things where you need to specify, for example, KV routing. What routing to use, right? Round robin, random, KV smart routing. Planner is enabled by default. However, it's a no-op by default. If you want to see the power of it, you just need to provide either CLI command, planner no operation equals to false, or just go to the YAML file and change the approach. Change the same config basically there. We do recommend to use the latest release simply because this is a very active development happening. Main branch may not be stable. At some points, we try to fix it as soon as we see it breaks, we try to fix it. However, for the best user experience, we do recommend you to use the latest release. I provide the git checkout command for your for the ease of the tryout. Multimodal, how multimodal are deployed? So we have multiple examples. In those examples folder, we do provide examples with 3 different models. So Qwen 2.5, Lava model, Phi3V, and the approach is the same. You use with the same command, you use Dynamo serve, you provide an entry point in your graph, and then the YAML file that specifies the config. There are more things happening underneath. I do encourage you to go there and explore it. It's very nice. So what's happening underneath, what the graph is and how does it work? So when the user query comes, it hits the HTTP frontend. And the task is for the frontend is to pass it down to the processor, and where the incoming request is actually will be converted. So tokenizer will be applied, chat template, if available, will apply. Then it's sent to the decode worker. Why does it send to the decode worker? Well, LLM, multimodal LLMs currently are examples which are built on top of VLLM. And in VLLM, decode worker decides whether it wants a separate prefill or not. So you can disable this disaggregated serving with decode and prefill, and then basically you can think about decode and prefill as happening in one place. The encoding is still separate, so image URL is going to be sent to your encode worker. And I'm mentioning how it's done in the example, so if you would like to change something, you're free to change it. Those are just reference implementations. So your image URL will be downloaded, and then a proper embedding will be computed and sent back to the prefill worker, which will incorporate it into the request, compute KV caches and attention maps, and send it to the decode worker. Decode worker will generate the decode tokens, and based either it's streaming or not, either one by one or all together, it's going to be sent back to the processor. Processor will encapsulate it in OpenAI compatible response, send it to the front end, and the front end will send it back to the user. So multi-node deployment. Multi-node is a bit more complicated in the sense of the setup, but not much. So what needs to be done is we need to start Dynamo distributed runtime services, right? And we provide one simple command that does that. You can also start NATS and etcd separately. We'll also provide the easy guides which you can follow to do that. It's just 2 commands, basically, to start NATS and etcd. And then on node 1, same as before, you just start your graph, start your front end. And then on node 2 and node 3 and any nodes that you want to use, what you do is you just need to specify your NAT server address and etcd endpoint addresses and put it into environment variables, which would be picked up, and then the communication will happen. And here in the multi-node deployments is basically up to you how you want to use it. Do you want multiple prefill workers on different nodes, or you want extra decode workers? That doesn't really matter. And here is also an example that all these graphs does not need to be started with the front end. You can start your workers separately, just specifying what you want to start. You want to start prefill worker, you want to start VLM worker, you want to start a separate processor. It's very easy and user-friendly. So what's NVIDIA Dynamo today? So we have a GitHub repo where we have Dynamo and Nixo. We also have our, I believe, enhancement documents. I'm not sure if they're shared or not. But if you're eager to see like all the proposals, they should be there, but I would double check. We have Apache 2 license and public CI, again, for user friendliness, for easy of contribution, right? You submit your PR, you open up your PR for the review, the public CI will start and you will see what's failing. Maybe it's simple links, maybe some internal tests are failing. You will be able to see that and fix that. We have pip wheels, so pip install AI Dynamo is there for you. Again, as I mentioned, we use Rust. Dynamo is Rust native, but Python friendly. We have Python bindings. We also have Discord for developer community, so if you have questions, GitHub issues is not the only source of reaching out to the developers. We also have Discord, and that's available through the Dynamo front page README. With Dynamo CLI. So Dynamo Serve, you saw me showcasing you how to start and deploy your graphs. There is Dynamo Run. So Dynamo Run is a very nice And easy CLI command, well, first to check whether your installation works, but also it uses a lot of the Rust core underneath. So if you want to start exploring Dynamo, I would recommend to go and explore how Dynamo Run works. So it supports text inputs. It's basically gonna, with this particular command I shared, it will start text chat in your command line. It also supports HTTP front end so that you can send your curl commands there. Very powerful tool. Supports batch processing as well. You can use Dynamo run -- help, and it will showcase you the list of everything. So Dynamo Serve, we went through Dynamo Serve. It's the tool to deploy your graphs. We also have support for Kubernetes deployment. So Dynamo Build, Dynamo Deploy, and Dynamo Cloud. I recommend you to check out those links. It's still an early release, but we're getting there. So Dynamo Build and Dynamo Deploy, I think it's in a very nice stage to try. Currently, we support 3 backends, TRTLM, VLM, SGLang. Disaggregated serving is supported with TRTLM and VLM. Stay tuned for SGLang support. KV-aware routing, same, supported for TRTLM and VLM. Stay tuned for SGLang support. We're working on a dedicated KV communication manager library, which allow you to do powerful things, as I briefly discussed, meaning like when your KV cache are computed, they can be transferred to whatever you want. You can transfer them to host, you can transfer them to SSD, and also the network level transferring. Nixel for RDMA and TCP. For the ease of reach, we have a shortcut, so nvidia.com Dynamo, and it will send you straight to the GitHub. If you want to contribute, you are really welcome, simply because there are so many things to do and not so many people to work on those things. As you can see, this was a recent screenshot on either Saturday or Sunday. So we have 99 closed external contribution PRs there in there. So every single one of those contributors is now a part of Dynamo development community. We're also working closely with 32 open issues. If you don't know where to start, we have this flag called Good First Issue. Just filter all the issues, take a look. If you would like to approach that, you're free to go there and leave us a note that you want to do that. You can even propose your ideas. We have people who actively monitor our GitHub and issues, and there is a bridge and communication with open source community and internal developers. So on that, I think I rushed at some point, but yeah. Thank you so much for coming to this talk. Again, thank you from me and from Ryan. We're happy and we're looking forward to see you contributing to the Dynamo. If you have any questions, I'm happy to take them and answer. Thank you. Oh, yeah. Oh, sorry. Go ahead.
Can you shed some light on if there are other players who are in the same space as Dynamo?
Yeah. So the question was, are there any other players in the same space as Dynamo? So VLM Stack has their own distributed data center solution, of course. They support, it's a separate folder, so they have a dedicated VLM framework and they have a VLM Stack. They're actively developing it. I believe LLM D is also sort of the same as a distributed solution. There was a mention of LLMD today at the keynote speaker. They currently support VLM. I'm not sure if they're going to support any other frameworks. The beauty of the Dynamo is that we don't really differentiate. We have VLM, we support SGLang, we work closely with the VLM and SGLang community recently. I think VLM 090 will have had merged our contribution and patch for the Nixel communication. And it was a collaboration between NVIDIA internal engineers and VLM representatives, so it was a collaboration that made it in. So we don't need to use the VLM patch anymore, which is quite nice. Yeah, I think those are two of the main players and the main friends, and really looking forward into benefiting the distributed data center scale solutions and see where it's going to get all of us to. Mm-hmm.
Is this being used by NVIDIA in production workloads today?
So I'm not sure how broadly I can share if it's internally. We definitely have our own benchmarkings, and we share benchmarking script, which you can try. That means like we deploy it internally as well, and we're making sure that everything works, everything performant, and we also share the production steps how to do that, and everybody can take it and use it, right? Yeah, you're welcome. Thank you so much for your question. Yeah. So the question is, this is the cloud level solution. Are there any developer? Does it fit well into development workflows? Can you clarify the development? Oh, yeah. So, so if I think one of the important things for that is also observability, right? So how can we plug it in? We do have the Dynamo logging, which is support. On the roadmap, we do plan to support, like we have metrics, like some of the metrics support, which you can plug in with Prometheus and have Grafana dashboards, right? We do support that. And we're actively working on making like this as a better support. There is also a roadmap on the issues where you basically can see like what directions are currently outlined so that it would be actually production-ready solutions. Like we're mostly there, but of course everything is missing. And like actually observability is a very nice point as well for contributions like OpenTelemetry. You can hook in OpenTelemetry, very nice tool. I was adopting it in Triton Inference Server, really like it. So yeah, thank you for the question. Yeah, question.
So how the Dynamo model will handle communication overhead, such as network card or PCI bus?
So the question is how Dynamo handles communication overhead. We actually outsource it to Nixel. We have a dedicated team working on Nixel and making sure the communication overhead is as small as possible inside the graph. I do encourage you to go into the dedicated Nixel repo and take a look how they do that. They support multiple backends like UCX and some other presented on the slides, but they also support custom backends. So if you want to plug in something that you really like, you're more than welcome to either fork the repo or contribute. So again, thank you so much. I think we're at time.